last example that I'd like to talk about here, I would like to find the area bounded by y equals x cubed plus 1 and y equals x plus 1. This one I do think is pretty tricky to graph, so I'm going to go ahead and graph it again. But you may want to just hit pause on the video and see if you can try graphing that one for yourself, just to see if you can do it. If you can graph this one, I think you'll be good to go. And of course, yes, you can use your graphing calculator to help you. What you would see if you graphed these two functions, think about this, y equals x cubed plus 1. That's just the cubed function shifted up by 1 unit, so you would see something that looks like this. And then y equals x plus 1. That means my, for this line, my y-intercept is 1, my slope is a positive 1. It's going to look something like this. And I have a new and interesting problem to worry about here. I have this shaded region to find. I have this shaded region, and I'm not sure what are they talking about here? They didn't give me an interval. So here's an instance where I do have to use two separate definite integrals. And I had alluded to this earlier when I said, hey, we need to worry about that point of intersection. Because if we have a point of intersection, like we do here, we have to break this up and we need to write two separate definite integrals. Because if you look, the upper and the lower functions switch. On the left-hand side over here, the upper function is the black curve, the lower function is the blue curve. But if I jump over to the positive x-axis, there it switches. Now the upper curve is the blue curve and the lower curve is the black curve. So we want to make sure that we split this up. We're going to need two separate definite integrals. So let's find our points of intersection first. Because they didn't give us an interval to work on, we do have to find the points of intersection. So I'll take x cubed plus 1, set that equal to x plus 1. Well, if I subtract 1 from each side, that's going to cancel. And here again, I know I don't want to divide by x, so I'm just going to set this equal to 0, so we'll subtract x. That gives me x cubed minus x equal to 0. Here I can factor out an x. That'll leave me with x times x squared minus 1 is equal to 0. Over here I end up with x equals 0, and x squared minus 1 equals 0. Solving this gives me x squared equals 1, or x equals plus or minus 1. So I have x equals 0 and x equals positive and negative 1. And this hopefully makes sense if we're looking at the graph. We actually have 3 points of intersection. We've got a point of intersection right here at negative 1. We've got a point of intersection right here at 0. And we've got a point of intersection here at 1. So I'm going to need, I said, two separate definite integrals. So let's break this up. Let's talk about the left-hand side first. On the left-hand side, and how am I even going to write? Left side. On the left side, we have, let's see, where our interval would be negative 1 to 0. So negative 1 to 0. There, my upper curve is the black function. Remember, we said that was x cubed plus 1. So my upper function is x cubed plus 1. Minus my lower function is the blue function, that is x plus 1. So I'm going to start with this. And then whenever I find that, I don't necessarily have to do both of these at once, but I want to show what we end up doing here. Eventually, I'm going to want to add the integral for the right side. And let's just set that up so that we have it. So let's see, that interval is 0 to 1, but this time my upper and lower function have switched. Now my upper function is this blue line right here. So now my upper function is x plus 1 minus my lower function, that black curve, that is x cubed plus 1 dx. So this is my right side. So I'm trying to evaluate these two separate definite integrals, and then once I have the results, I'll just add them together. So let's work with the left-hand side first. I'm just going to rewrite the problem down here, -1 to 0. We had x cubed plus 1 minus x plus 1 dx. So first thing we'll want to do is distribute this minus sign. Make sure that you're using parentheses here because I do want to distribute that minus sign to both terms. So here I should have the definite integral from -1 to 0. X cubed, 1 plus -1, these two will cancel, so I just have x cubed minus x dx. So let's see, I want to find my antiderivative. This will be x to the 4th over 4 minus x squared over 2, evaluated at 0 and at -1. So this will be, let's see, 0 to the 4th over 4 minus 0 squared over 2 minus -1 to the 4th over 4 minus -1 squared over 2. So here 0 to the 4th over 0, that's just going to be 0, and 0 squared over 2, that's just 0. So I have 0 minus, let's see, -1 to the 4th, that'll be a positive 1 over 4, minus here, again, I'll have a positive 1 over 2 this time. If I get a common denominator, I've got 1/4 minus 2/4, give me opposites -1/4, -1/4, which would be a positive 1/4. So, okay, I've done a lot here, but that means that the definite integral on that left-hand side, this has a value of 1/4. So now, I just need to find the definite integral on the right-hand side. So let's scroll down so that we have enough room. This time I'm going to integrate from 0 to 1. We said our upper curve this time was x plus 1 minus x cubed plus 1 dx. Again, make sure you're using parentheses here because I want to make sure to take this minus sign and distribute that to each term. Because that's what tells me 1 plus -1, those two will cancel. So this time I'm left with the definite integral from 0 to 1. I've got x minus x cubed dx. This should look pretty familiar. So I have x squared over 2 minus x to the 4th over 4, and I'd like to evaluate that at 1 and 0. So let's see, I've got 1 squared over 2 minus 1 to the 4th over 4 minus 0 squared over 2 minus 0 to the 4th over 4. And once again here, 0 squared over 2, that's 0. 0 to the 4th over 4, that's going to be 0. Please make sure you double check your work and make sure that that is the case. Here we're working with a polynomial, so it is. We don't need to worry about it. And let's see here, I've got 1/2 minus 1/4. We looked at this earlier. We said this is 2/4 minus 1/4 or 1/4. So hey, 1/4 once again. What do you know? Who could have guessed? So that means that the right-hand side is also 1/4. So now I'm saying 1/4 plus 1/4. Well, that's really 2/4 gives me a total area of 1/2. So once I add these two together, that gives me the total area bound by those two functions. That's what gives me that yellow shaded region in my picture up here. The two yellow shaded regions together have a combined area of 1/2. So this one is very tricky. I won't ask anything like this on the exam, but it is important to make sure that you check for those points of intersection, because if you have more than one point of intersection, or if you have a point of intersection in your interval that is given to you, then you do have to split that up into multiple integrals. So just something else to keep an eye out for. And that's all I got for this section. So when we come back in Chapter 7, we'll actually be done with integrals for right now. We're going to come back and we've got one last hurrah for derivatives. So we're going to jump ahead and start to talk about three-dimensional functions and partial derivatives in Chapter 7.